Hello. So let's talk about dynamical systems. So the first thing is, what is a dynamical system? Dynamical system, so first off, this has many applications used in dynamical systems courses and control courses and robotics courses. So the first question is, what is a dynamical system? So dynamical system is a system whose state evolves with time. Now the question is, where do we get these states? State describes the configuration of the system, for example, in mechanical systems. But when we say dynamical systems, we are not necessarily talking about mechanical systems. It could be electrical systems, electromechanical systems, biological systems. They are all dynamical systems. Any system whose states evolves with time, is a dynamical system. And the question is. And then mathematically, so the question is, where do we get that model of the system which describes the change in states of the system? So because we need to somehow describe how those states vary with time. For example, if you have a mechanical system, your question would be, for example, how velocity or acceleration vary with time. If you have electric circuit, you would ask, all right, how would charge and voltage vary with time? So those are states. If you have a biological system, for example, then you would ask, how would, for example, the population of a species change with time, evolve with time? So there are two ways we can describe and find the model of the system. We can use physical principles. So physical principles, the most important one is, for example, Newton's second law. We can use Newton's second law, describe, for example, how the states of a mechanical system varies with time. We can have experiments. So we can perform experiments and measure how would the population of a species change with time, and then describe them mathematically. So we start with this experiment and then devise the mathematical model. So we either start with the physical principles like Newton's second law, or, for example, experiment. So, for example, to further clarify these basics, so if you think about this simple mechanical system, this spring, mass, and force, it's pretty obvious how we derive the equation of motion. So in this course, it is assumed that you know how to apply Newton's second law to this system. If you apply Newton's second law, you get mx double dot plus kx equal F. F being the external force. Now, if I go and say let my x being equal to x1, and then x1 dot, which is x dot, equal to x2, I can describe this equation as x2 dot. So remember, this x2 dot is in fact equal to x double dot. All right. So same thing as x double dot. So we have this x2 dot equal to negative k over m divided through by m, k over mx1 plus f over m. So if you think about it now, if we ask you now to describe this system, this dynamical system, you would say, my dynamical system is x dot. Now my x is my state vector, and x is x1 and x2. So x dot is f of x, agreed, and the external function. So in other words, what I've done here is that we got rid of the second order differentiation with respect to time, and instead of having a second order ordinary differential equation, I'm going to have a bunch of first order differential equation, first order coupled differential equation, because I have to describe this system as x1 dot equal to x2 and x2 dot equal negative k over m x1 plus f over m. Great. So in general, if I had n states, my dynamical systems equation is going to be x dot n by 1. Now, remember, this is not just a mechanical system, and this is not just a three-dimensional space. So this n could be larger than 3 because it could be an electromechanical system. So x dot, so I have you give me my your electromechanical system. You use the physical principles. You use, for example, if you have an RLC circuit coupled to the motion of beam, for example, a mechanical beam, then you would use Newton's second law as well as your Kirchhoff's current law, for example, and then you write down the mathematical equations describing how the states of the system evolve with time, and then you end up having this general form of a dynamical system, x dot n by 1, f of x and xt, and u being my, for example, external force, or my input. And as I said, a dynamical system also could be a biological system, but the difference is, pay very close attention here, that the state vary with time. But the way we describe that change with time is not necessarily the differential equation. For example, if I say that, or the population of this species would increase such that after 1 year, after each year, the new population is going to be 150% more than the current population, or 3 over 2 times current population, then you would use a difference equation just like this to describe how the state of the system, in this case the population, change with time. So we are dealing with two types of equation. We are dealing with the difference equations and differential equations. So both difference equations and differential equations are used in dynamical systems. And then we talked about RLC circuit, for example, another example of a dynamical system. So, all right, so now let's consider this type of dynamical system. This type of dynamical system, I have x dot f of xt. So I'm not having, in this case, I'm not having an external force. So in general, you could have here, you could have your external input. You could also include your time if, for example, your external input explicitly depends on time. You would include the time. Or you would have this case where x dot, the evolution of this state with respect to time, is a function of xt. Now I'm using this under arrow to show that this xt in general is an n by 1 vector. Agreed? Because, as we said, again, it could be current, voltage, and velocity and acceleration. So you could have 4 states describing the state of your total electromechanical system. All right, so one more thing here. So if you pay very close attention here is, so one question is, why do we need initial conditions? If you remember, if I give you a differential equation, you would ask me, what is the initial condition? Because if every time you solve a differential equation, you would need an initial condition to determine your unknown coefficients. So you would ask me what the initial condition is. Once I give you the initial conditions, you apply the initial conditions, and we're going to see this later. You're going to apply initial conditions and find the solution to your differential, to your dynamical systems. So when we say solve the dynamical systems, it means that you solve for the general solution, and then you apply initial conditions and find the solutions we're looking for. The other thing, the last thing here is any point. So if you pay very close attention here is, again, from your calculus, you know that if I'd asked you to compute the tangent to a vector, you would have differentiated that the curve at any point, and you would have given me, by evaluating that tangent at any, that once you differentiated the curve at any point, you would have evaluated that and given me the tangent to the curve to that point. So if you look at this equation is already in the form you're looking for if we were looking for the tangent to the curve, agreed? Because we already have it in x dot form. So if this curve, for example, in 2D, because I'm using 2D here because in 2D it's easier to visualize the solution. So I have already solved this system, found the solution to the system, applied initial condition, and found that this is a curve describing the solution to this dynamical system. So once I give you this, I say at point A, then what is the tangent to this curve? You say, all right, so I'm going to differentiate x1 dot, differentiate x1 with respect to time, and then differentiate x2 with respect to time, and x2 dot, and I'm going to have x1 dot and x2 dot, and this vector describes the tangent. So x1 dot describes the change along horizontal axis, in this case x1. x2 dot describes the change along vertical axis, x2 dot, and the total change would be x dot. What is x dot? X dot is equal to fxt. How do we determine x dot? At A, we evaluate f at A. So A, let's say A is x1 hat, x2 hat, the coordinates of A. When you evaluate the right-hand side, it gives you the tangent. Now, this tangent is unique. You cannot have two tangents to the solution of your dynamical system at one point. Agreed? Because if so any point, the tangent is determined by the vector field. So if, for example, if you had two, so for example, think about it this way. So I have to rephrase my question. I have to ask my question this way. Could we have two curves, two solutions going through the same point A? For example, could I have a solution like this? We cannot have two solutions going through the same points, because then at that point we're going to have two tangential vectors, while our tangent vector is defined by this function and it is unique. All right, thanks for paying attention. See you next time.